Welcome and hello. This is a video exercise using the FHWA hydraulic toolbox. I'm titling this exercise Long-Term Degradation of Bridge Scour by Armoring. So what we're going to be doing is creating a project in FHWA and then importing that project into our Bridge Scour calculator and within the hydraulic toolbox. And then calculating the Bridge Scour using the armoring method. All right, so let's go ahead and get started. Right now I have my hydraulic toolbox on the screen. I'm going to right click on my project and add a new bridge scour analysis and then double click to open up that dialog box. This is the calculator, and the first step is to import a cross section from a FHWA file. So check the checkbox here for enable scour plot options and then import geometry from FHWA file. Go ahead and click on import. And now what we need to do is browse to that FHWA project file. Now we haven't created it yet, so that's what we're going to do sort of in the first half of this exercise. And then we're going to come back to this dialog box, import the FHWA project, and then continue on with our bridge scour calculations. All right, so without further ado, let me fire up FHWA. I'm using 6.6, but most any version should work fine. I'm going to go ahead and create a directory dedicated for my FHWA project files inside my main project directory. So there's nothing in here right now. This is going to be the destination directory where I saved my FHWA projects. So here's FHWA once again. I'm going to go File, New Project, and then navigate to that folder that I just created. All right, after some navigating, I am almost there. Projects and FHWA. Okay, I'm just going to call this project, something very generic, and okay. This dialog box is just telling me that I'm using US customary units, which is what I have set to default. That's what it says right here. But if you're using metric units, you can go up to options and then unit system, switch it over to metric system. I'm not going to do that, so I'm just going to keep it at US customary. Click OK. I'm also not going to describe everything there is to know about FHWA. So if I'm being a little bit too brief in my descriptions, you're welcome to ask a question. And I've got a number of FHWA videos as well. Okay, so let's go with edit. Open up the geometric data editor. I'm going to start by sketching in a river reach. So I'll just do some single left clicks in the downstream direction. Double click to terminate the reach. And then whatever I call it here, I'll call it river A, reach 1. Not too important for what we're doing here. And then cross section is where we are going to create the cross sections first. After that, we'll add the bridge that goes over the river. So to start, we'll create our first cross section by going up to options, add a new cross section. We'll start at the bottom of the reach, which is river station 0. Click OK. And then I'm going to just paste in some station elevation values, which I had saved to my clipboard because I had them prepared over in an Excel file earlier. So this is the cross section looking in the downstream direction at river station 0. The distance to the next downstream cross section 0. The left overbank Manning's number is going to be 0.05 and then 0.035 and 0.05. Those are just some typical roughness values. And then the left bank is going to be 30, and then the right overbank station is going to be 90. So I'll type those numbers in here and then click on Apply Data. So here in the side, we have a preview of the cross section. So it is symmetrical. It's centered on station 60. You can see the Manning's end values across the top. If you don't see this view, then you can just toggle it on or off using the button right here. And if the FHWA process that I'm describing is totally new to you, I'm sorry, but I will leave a link in the description where I describe this process in a little bit more detail. That will be to a lesson on the FHWA hydraulic toolbox. So take a look at that. All right, so this is the first cross section. I'm actually going to create 4 cross sections. So 2 will be downstream of the bridge, 2 will be upstream of the bridge. The next one upstream will be river station 200. So I'm going to copy the current cross section. It's going to be on the same river and the same reach. It's the only river and reach in my project, so that's easy. River station 200. I click OK. And then I'm going to say it's 200 feet downstream to the next cross section at river station 0. And the other thing I want to do is add some elevation. So these elevation values are going to increase by, let's go 1%. Okay. excuse me, 1 foot. So that would be 0.5%, since it's 1 foot of rise over 200 feet of run. Yes, that's correct. All right, let's go ahead and add a couple more cross sections. So I'm going to make a copy of the current cross section. This is going to be at river station 300. I'll click OK. So the distance to the next downstream cross section is now 100, 100, 100. And that is all we need to do. I'm going to say no change in elevation here. So apply data. And then one more cross section is going to be at the very top of the reach. This will be at river station 500. So click OK. That is going to be 200 feet upstream of the previous cross section. So 200 and 200. And then I also want to increase the elevation a little bit more. So adjust elevations. This is going to be an increase of 1 foot for another 0.5%. Okay, I'm going to go plot and then plot profile. Oops, yes, I want to save changes. There we go. And then we have the 0.5% flat, 0.5%. So it's much flatter than it looks like. It's probably, yeah, even flatter than that. And then our bridge is going to be right here. I'm going to put the bridge at river station 250. It's going to be centered at 250, but it's going to be 80 feet wide, so that it's going to be 10 feet between the upstream bridge face and this cross section of 300. And then the river station cross section at river station 200 will also be 10 feet downstream of the downstream face of the bridge. Okay, I think I said that right. Let's just go ahead and build the bridge and you'll see what I'm talking about. Then I'll go ahead and close this. So we see our cross sections have been placed on the plan view in the geometric data editor. I'm going to click on bridge/culvert and then options, add a new bridge. This is going to be labeled 250 just because that's where I'm going to center the bridge. And then click OK. All right, so we have the upstream of 300 and the downstream of 200 cross sections, which should be identical as far as the station elevation data goes. And then I'm going to add a deck/roadway. So I'll click that button there. The distance to the next upstream cross section is 10 feet. The width of the bridge will be 80 feet. I already talked about that. And now we need to define the station, high chord, and low chord for both the upstream and the downstream. I have some numbers prepared in Excel, so I'm just going to paste them in, and then you'll see what they are. So the low chord is 65 feet, the high chord is 70 feet, and that's for the entire station length of the bridge, 0 to 120 across like this. So I'm going to also copy that data from the upstream to the downstream, and then let's go with an upstream and downstream embankment slope of 3 to 1. Okay, so if I click OK, and then sort of resize, there we go. If you just kind of have to agitate the dialog box a little bit for it to update, we see the deck/roadway sketched in right here. Now for this exercise, I'm not going to be analyzing pier scour or abutment scour. I'm just going to be doing long-term degradation, in which case I'm not even sure if I needed a bridge or not, but I've already added it. My point is I'm not going to make any more changes to the geometry. I'm going to save the geometry, add a constant flow file for a steady flow simulation, run the simulation, and then be able to reference it from the hydraulic calculator. All right, so enough of this bridge building operations. I'm going to click on close. And then we can see the bridge has shown up in the plan view right here. So that looks correct. I'm going to save my geometry file. So I'll just go save. I'll title this base, and then click OK. You can call it whatever you want, but that's cool. All right, let's go ahead and add some flow data. So steady flow data. There's no need to get fancy with unsteady flow. I'm going to say 5,000 CFS for my one and only profile. In fact, I'm going to rename this. This is sort of optional, but kind of nice. You can go edit profile names, and then instead of PF1, you can be a little bit more descriptive and say Q equals 5,000 CFS, and then click OK. All right, so that's showing up here in the table, and it would also show up a number of other places in plots and diagrams and results tables. I also need to set the boundary condition at 0.5% slope. I assume this is subcritical, so I'll just use the normal depth of 0.005 and OK. That is all I need for the flow data. Go File, save that. I'll call it base as well. We can close, and then I'm going to run steady flow analysis. Here is the dialog box. We're going to assume subcritical. For the base geometry file and the base steady flow file, it's only appropriate to call this plan base as well. So save it, and then we'll call this base, and the short ID is also base. All right. click on compute, let that run. It's done. Click on close. Let's take a quick peek at the results. One of the fan favorites is cross section. So here is the cross section at the bridge. This is the upstream end of the bridge. If I go further upstream, this is river station 300. This is river station 500. And then it repeats. So we're down at the bottom now. River station 0, 200, 210, the downstream face of the bridge. This is 290, the upstream face of the bridge, 300 and 500. I am going to double check to make sure our brood number is less than 1. So profile summary table, 0.6, 0.5, 0.7. That looks good right there. That's all we need to do for the HEC-RAS. I'm going to keep it open because we may need to reference some other results. But for now, I'm just going to minimize it. And then back in the hydraulic toolbox, we have the bridge scour analysis. I'm going to browse for that HEC-RAS.prj file. Boom, here it is. And I have all of my cross sections should now be available to select. And cool, here they are. So the approach cross section is going to be the upstreammost cross section at river station 500. And it looks like the data came in. There's 8 points. And then the bridge cross section, the upstream face was 300. And then the bridge itself is at river station 250. Now, I don't have abutments. I don't have piers. I don't have to deal with anything else with that right now. I'm just going to click OK. And now our dialog box has exploded with lots of options. I'm going to uncheck a number of these bridge scour options, and I'm only going to check on long-term degradation and then click on define. Now, the two different options are controlled by armoring and controlled by equilibrium slope. I'm only interested in investigating controlled by armoring for this exercise, so I'm going to select that one. And then for our results in a little bit, once we fill out some numbers, we'll get a critical grain size as well as the armoring thickness for the amount of degradation that will occur based on our input data. Okay, so shields parameter, this is a value that depends on the soil itself. For a typical sand, the user's manual says to use 0.047. So let's go with that. The hydraulic radius and the average channel velocity, these are values that are going to be, okay, hold on a second. I just noticed that we have metric units. So let me just click OK and change that. I need to click OK, see units, US customary units. Okay, back to the bridge scour calculator. Define long-term parameters. Okay, looking good. So we're in length is now in units of feet, and then velocity is now in units of feet per second. Okay, so where were we? Hydraulic radius and average velocity. Let's go ahead and get those results from HEC-RAS. So I'm going to go up to view and then profile summary table. I'm going to change the standard table from standard table 1 to 6 cross sections associated with a bridge. Here we go. So it's all using the same 5,000 CFS, but each row here represents a different cross section, including the upstream and downstream face of the bridge. So it's labeled 250 and 250, but keep in mind that the width of the bridge is 80 feet. So it's really 210 and 290. It'd be kind of nice if there was a way to modify that. But so the channel velocity is right here, but we're looking for the velocity for the entire cross section, not just the main channel. And we also want to know the hydraulic radius for the entire cross section, specifically this cross section right here, which is the upstream face of the bridge. You can make edits to this table if you go up to options and then define table. And what I'm going to do is scroll over to the far right. I don't want average velocity in the main channel, so I'm going to delete that. But what I do want is the average velocity for the entire cross section. So I'm going to type in velocity. This last one here, vel total, average velocity for the flow in the total cross section. I'm going to click on column 10 and then double click on that variable. Okay. And then the other thing I want to look up is the hydraulic radius. So radius. And then for column 11, hydraulic radius for the entire cross section is right here. Okay. So these are the two values I want to pluck out and use for my bridge scour calculator. So we're looking at 9.33 and 5.99. That's the velocity in feet per second and the radius in units of feet. Back to the hydraulic toolbox. And where were we? Radius is going to be 5.99 and the average channel velocity is 9.33. It says channel velocity, but I think it means entire cross section as opposed to the main channel. HEC-RAS seems to be a little bit more specific and precise in its terminology than the bridge scour calculator I've found. Okay, let's just continue on though. Unit weight of water, 62.4, that's typical of fresh water. And then the unit weight of the sediment, let's just stick with the default there, 165. All right, Manning's N value, 0.035 is what we use for the main channel. However, there was some flow in the overbank, so I think we should increase this number a little bit to account for that overbank flow. How about 0.038? And then the armor thickness factor, let's stick with 2. All right, so once our numbers are in, we have some results. I also forgot to mention coarse bed material needs to be selected. And for a D84, let's go with 1 millimeter, just a nice round number, and then tab off. And okay, boom. Here are our results. The critical bed material is 0.073 feet. So that would be a little bit less than an inch, I think, but that is dependent on a number of these parameters. So if it was a finer sand, such as 0.1 millimeters, then I tabbed off. The critical bed material is now about 2/3 what it was, down to 0.0458, which is just more than half an inch. Okay, that kind of makes sense because 9 feet per second is pretty fast, even though it's just a 0.5% slope. And then the last thing to add here is the percent of bed material coarser than the critical material size, this D sub C. So if I went ahead and entered 100% and then tabbed off, we would already be fully armored, meaning the depth of degradation is 0. There's no degradation that's going to occur. But if I went ahead and changed it to, say, 10% and then tabbed off, it looks like 0.82 feet of degradation would occur. And probably a more normal number, depending on the material, is something like 3%. So if I tab off, now it looks like as much as 3 feet of degradation would occur until the armoring would be fully developed. So anyway, those are the results. We have the depth of degradation. This is the long-term degradation that's controlled by the armoring method based on our hydraulic radius, the channel velocity, the shields parameter, the gradation of the soil itself. And of course, we use HEC-RAS and the bridge scour calculator, specifically long-term degradation method, to calculate the bridge scour using the FHWA hydraulic toolbox.